we designed two pads for regulator because it has 3 pins and we need to differentiate the first pin. And also we designed two pads for the temperature sensor and also for LED because LED including 2 pins, one positive and one negative. For the operational amplifier LM741 we designed 2 pads also because we need to differentiate the first pin, which is pin number 1. In today's lab we will continue designing our project by designing the footprints and to get the footprint dimensions from the data sheets. So the dimensions of those components here, we can get them from the datasheet. Just to remind you how to get those dimensions, we will go to DigiKey website, digikey.com. Then we will search for the component that we need from here. And the components, it should be through-hole components because our project is to design a through-hole components over a printed circuit board. So we will design a footprints through-hole footprints for this components. And we will get the dimensions of D, E and E1, and sometime we need E small and E1 small in case of operational amplifier because we have some different dimensions as we will see. In today's class we will design 3 footprints for the battery, for the resistor and for the regulator, and next lab we will continue with designing the footprints to design for temperature sensor, for LED and for operational amplifier. So let's start with a wire to board connector or the battery connector. We need to get the data sheet from again the DigiKey website, the same thing we did in lab number 4 and lab number 5, the same way of design. You will go to digikeywebsite.com. You can also refer to recording of lab 4 and lab 5 to see how we get the data sheet, how we calculated the pads dimensions and the footprints dimensions. So from the data sheet we got the dimensions of D, E and E1 to be 9 mm, 10 mm and 5 mm respectively. Also I got the dimensions of the resistor footprint to be D to be 2.6 and E to be 6.3 and E1 small to be 28.1 mm. For the regulator LM7805 we got the dimensions of D to be 15.95, for the regulator 4.7, and for E to be 10.67 and E1 to be 2.54 mm. Again, to get those dimensions you have to go back to the datasheet. From the datasheet you will find the place where you have those dimensions, and after that you will open the PCB editor software to get to know what's the dimension D and what's E and what's E1 and to compare it with the datasheet. However, in the revision week, which will be next week, I will do again another examples or exercise how to get the dimensions of different components from their datasheets. So now what we need to do is to apply those dimensions that we get from the datasheets into the PCB editor software, and we need to create a package symbol wizard for each one of those components 1, 2 and 3. And next lab we will continue with footprints of 4, 5 and 6. So the thing that we need to do now is to open the software PCB editor. I will open the software now. So here is our software. Just to remind you what we were doing with the software, the thing that we need to do here is to design the footprints and also to import the pads which we designed last lab inside this software, which will help in design of footprints. And also we need to design, after we finish design all footprints, we need to design a board and to connect between the components based on the schematic which we have in the first stage of designing of this project. Then after that we will create a Gerber files, outline files, and drill files in order to be able to fabricate or to print the printed circuit board using the milling machine. So the thing that we need to do now is to start designing using the dimensions that I posted or I just showed. Also, you will find those dimensions posted on the Moodle page of your course. Okay, so I will start design the wire to board or battery connector again with the dimensions D equal 9, E capital equal 10, and E1 equal 5 millimeter. So we will go to File, New, and we will choose Package Symbol Wizard from here. Remember that you need to save the files, all footprints, inside the same folder that we created last time, and inside this folder we saved the paths of those components. So we have to save this file inside the same place we saved last time. I named it Fire Alarm Project Spring, so I will name this, we will design for the battery, so I will name it, let's name it wire, because we named the pad to be wire and we have two pads, one circle and one square. Now we need to name it wire underscore footprint, so I will name it wire underscore foot. Then we will press on OK. Here you have to remember that we are designing for through hole components and we have here two pins, so I will choose from here through discrete, this one. Then we'll go next, from here load template, then next. From here we need to change to choose millimeter, and because we are designing for battery, it's better to give a prefix or designator to be B. Then next, here we need to add the dimensions. As we said, we need to add the dimension D, E capital, and E1. How to add these dimensions? As we said, we have to go to DigiKey website, find the datasheet of the wire to board connector, the same thing we did in lab number 4 and 5. Then from there you can get the dimensions, and I got the dimensions inside the Word file which I showed you 5 minutes ago. So we found that D equal to 9, E capital equal to 10, and E1 equal to 5. Remember that E1 is the distance between the pin and the pin. So when we have two pins, the distance between them, it will be E1. And E capital is the dimension of the body. So sometimes you will find that E capital more than E1. Sometimes you will find E1 more than E capital. It depends on the component itself. In our case here, we have the pins, the dimension between the pins less than the dimension of the body or the distance of the body itself. So here E1, E capital more than E1, and D is the width of the component. So I will just add the dimensions which I have. So I have D to be 9, and we have E capital to be 10. I'm taking these dimensions from the Word file. You can just open the Word file and find the first row in the table. You will find those dimensions, and E1 it will be 5 millimeter. Then we will go next. Here we need to add the pads that we created last class. If you have the files saved, the footprint files and pads inside the same folder, you will find them directly here. Otherwise you will not find them. So you have to make sure that you are saving the files inside the same folder. So from here I named the pad to be wire underscore circle underscore pad. We have circle for all pins and the square only for the first pin in case I have more than 2 pins. So I will find it here, and we need to differentiate pin number 1. As we said, the positive pin, it will be the square one, so I will add it wire underscore square underscore pad, this one. Then we'll go next, then next, and finish. Once you finished creating the pad, the footprint, you will find it here. As you can see, we have it, the first pin to be square and the other pin to be circle. So we will use pin number 1 to be the positive pin. And remember all the time to save your work, just to make sure that you save the footprint. So now we finished designing the first footprint for our project, which is the footprint of the wire to board connector, or the footprint of the battery. So here, the thing that we did, we designed this footprint. So just to remind you what we did here, we designed the footprint of this battery. As we did, we had D to be 9 mm, E capital to be 10, and E1 to be 5 mm. The next step now is to design the footprint of the resistor. For the resistor here, we have D capital equal 2.6, which is B inside the datasheet, and E capital equal 6.3, which is A inside the datasheet, and E1 small equal 21.8, which is C over 4 plus C over 4 plus the dimensions of the body A. To remember how we got those dimensions, just go back to lab number 4, also lab number 5. We retrieved those dimensions from the datasheet of the through-hole resistor for any resistivity we have, because we have the same size of the resistor. So let's again design the footprint of the resistor. And remember, last class we did the pads of the resistor and we named resistor underscore pad. We have only circular pads because the resistor we don't have positive and negative dimensions or pins. So here I will share with you again the software to start designing the footprint of the resistor. So again we'll go file, then new, package symbol wizard. We will save inside the same place and we'll name it resistor underscore. Now we need to design footprint, and we will use the the same we will use the same pads we designed last class. So we'll go OK, and again we will choose through discrete, then next, here load template, and next. From here we will choose millimeter, and we'll change the prefix to be R because we are designing for a resistor. Now we need to enter the dimensions E1, E capital, and D. As you can see here, E1 this time is more than E capital based on the Word file I showed you, or document that you can find it in the Moodle. E1 more than E capital because in this case the body of the component, the distance, the dimension of the body less than the distance between the two pins. So here it's a different story than what we did with the battery connector. So I will take the dimensions from the Word file. So D equal 2.6. We have D equal 2.6 millimeter. We have E capital equal 6.3. And we have E1 small equal 21.8. Just a hint for the resistor, because the legs or the pins of the resistor are very long, you can use a less dimension of 21.8. For example, you can use a double of or 3 times of the body size, so you can use 15, 18. It will work with you, and at the same time it will save space over the board. But for this time, let me use it to be as we did in lab number 4, to be 21.8. but it's not a mistake to use, for example, 15. It will work and it will be better even. Here we need to add the pads that we designed, so we name it resistor underscore pad. So this is the pad that we have, and we will use the same pad for pin number 1 also, because we don't have a square pad for the resistor. Next, next, and finish. And this will be the pad of the resistor, and the thing that you need to do here is to save your work, just to make sure that you saved the pad of the resistor. Later, over the board, we will retrieve those footprints over the board, so we have to remember the names. Once you forget the name of the footprint, just go back to the folder which include the whole footprints and pads, and there you will find the name of your footprint and the name of your pads also. The next step that we need to do, we finished designing the footprint of the resistor. Now we need to design the footprint of the regulator LM7805. I will show you once I finished designing the regulator. I will just do a revision with you about the data sheets of those components and how to get the dimensions from these data sheets. So we need to design the footprint of the regulator LM7805. I get the dimension T to be 4.7, the dimension E capital to be 10.67, and E1 to be 2.54. So we will create a new footprint from here, and we'll name it regulator underscore foot. And remember that we designed 2 pads for the regulator, one positive to differentiate the first pin, because the regulator including 3 pins, 1 input, 1 output, and 1 grounded. So okay, because we have 3 pins on the same side, in this case I will use SIP, because if you use the through discrete, as you can see here, you have only 2 pins, but for the regulator, as you will see in the datasheet, it has 3 pins, so I will use SIP. Then I will determine the number of pins in the next stages. So from here, load template, then next. From here we'll choose millimeter. Now for the regulator I cannot use R because I used it for the resistor itself, so I will use for example G here, just to show that this G meaning the regulator. Then next, here you have to add the number of pins. For the regulator we have 3 pins, so we will change this to be 3. We have 3 pins now, and we have to add the dimensions E small, E capital, and D. As you can see here, E small is the distance between 2 adjacent pins, E capital is the width of the component, and D is the length of the component. So from the document that you have, you will find that D equal 4.7, so D equal 4.7, and also E capital 10.67, and E1 or E small equal 2.54. This is the standard dimensions. In case you have more than 2 pins, the distance between the two pins, it will be 2.54. It's a standard. Even without to get it from the datasheet, you can put it like this. Now between E capital and D, as you can see here, we have E capital as a dimension less than D capital, but the thing that we have here, that E capital is more than D capital. Here it will change only the rotation of the component. So if you added, for example, 4.7 in E and 10.67 in D capital, it will not be a mistake, but the component, it will be only rotated. But from where we got those dimensions? Again, from the datasheet, we got the dimensions of our components. It's better to stick with this, but if you want to swap them, it will be also fine. Here we need to add the pads that we designed for the regulator, so it will be a regulator underscore circle underscore pad. It will come by default for the two pads here, but we need to differentiate pad number 1 with the square pad, so we will choose regulator underscore square underscore pad. Again, from where I'm getting those names, those are the names that we give for the components last lab. So just go to the folder you saved those components inside it. You will find the names there. You can get it from there. Okay, then I will go next, next, and finish. As you can see here, here is the square, here is the circle, and here is the circle. Now, this coming, as you can see, the width here is more than the length of the component, because I used those dimensions here, 10.67 for E and 4.7 for D. I will design it again, but I will swap now the dimensions. We will name it regulator 2. I will save this one. We will name it regulator 2, and later we can use any of them. Now, what's the difference between them? As we can see, we are interested only in the distance between the pins. So if you bring your regulator and put pin number 1 here, then 2 here, and 3 here, it will work with you. And if you rotate those components to be number 1 here, number 2 here, and number 3 here, it will work also with you. So we are just rotating the component. I will redesign this component to see which one it will be better with us. I will name it regulator 2, and I will give it a prefix G2, and later when we design the port, we will see which one will fit better with our design. But if you want to design only one, it's fine, it's okay, there is no mistakes. So again, I will design a new package symbol wizard. I will give it regulator 2 underscore foot. Then OK. Again, we will choose SIP, load template, from here millimeter. I will give it prefix G2. Then here we have 3. E small, there is no change on E small. The only change is between E capital and D. So I will give D to be 10.675. 10.675, and the E capital to be 4.7. This is 10.67, and E capital to be 4.7. Then next, here again I will add the same pads that I designed last class, so it will be regulator underscore circle underscore pad, and for this one it will be regulator underscore square underscore pad. Then next, next, and finish. As you can see here, only the rotation of the width and height of the component. I think this will be better for us, and it will save more area over the board. So we can use this one, G2, or we can use G1. We will see. I think it's better now to use G2 because it will save some area from here. So just save this one. And by this we designed, just a minute, let me back to the main screen. So by this we designed the wire to board connector, the resistor FootPrint, and the regulator LM7805 FootPrint. Now I will give you some time, like 15 minutes, to try to search for the data sheets of those components using DigiKey website. Inside this time, try to get the dimensions of D, E capital, and E1. So you have 15 minutes from now trying to get the data sheets of the battery, of the through-hole resistor, let's say with 1 kilo ohm, and for regulator LM7805. For the wire to board connector and resistor, again you can back to lab number 4. You will find I explained there how to get the data sheet and how to get the dimensions from this data sheet. And for the regulator, I will show you once you finished. I will try to explain you how to get the dimensions from the data sheet. So you have 15 minutes from now. Okay, again, let's see how to get the dimensions of the regulator. I searched for the datasheet of the regulator using DigiKey website, or you can just in the DigiKey website you can search for voltage regulator or LM7805, or just you can Google voltage regulator and you can find the datasheet. Now any voltage regulator, it will have very close dimensions. So for example, for this datasheet which I get here, this is the voltage regulator that we have, which I showed you in the first lecture of the project. So this is our voltage regulator. The dimensions that we need from here is the distance between two adjacent legs, this and this. As we said, you can use the standard dimensions, which is 2.54, or you can choose the maximum from here, which is 2.79. So it will, both of them, it will be working fine. We use 2.54 in our when we design the footprint. Also, we need the width of the component from here to here. As you can see, we have um, 10.16 plus minus plus 0.38 minus 0.23. As we said, we are using the maximum number, which means we are adding 0.38 to 10.16, and it will be very close to the number which we used from other datasheet. It was 10.6 something. And also we need the length of the component, or sorry, this is the length of the component, and we need the width of the component. The width, which means this part, it will be, we should reserve a place for this part over the board. So the distance from this point to this point here, it will be 4.7, the minimum 4.45 and the maximum 4.7. So we are using the maximum one, which is 4.7. This is in millimeter, and the upper dimensions here 0.18 and 0.17, it's in inches. So from here we got the dimensions of the dimensions of E capital and dimensions of E small. And also when we design the pad for this component, we need the dimension of the leg, because this leg, it will go inside the board. So we will search for the leg width, if we have it here, and we should have it here, in order to use it inside the board when we design this for the pad. And again, when you design the drill size, you will take it from here and you will make an approximation for the closest drill head which we have in our lab. And for the pad dimension, it will be double of the leg or the drill dimension. So this is how we design the footprints, the first part of designing the footprints. And next lab we'll continue with the remaining parts of the footprint, where we have let me show you what's the remaining here. Here we finished with the first, second and third one, and we need to design for temperature sensor, LED and operational amplifier. For the temperature sensor, in case we don't have the data sheet, and in our case we don't have the data sheet which includes the dimensions of the pads and the footprint, so in this case we will use the vernier caliper to measure the dimensions of this sensor. For the LED and operational amplifier, we can get the dimensions from the data sheets. So this is what I need to explain for you for today, and I will stop at this point, and next lab will continue from number 4, 5 and 6. Thank you very much.